So welcome to the fourth lecture of the third week of this course on machine learning. So we will talk about artificial neural networks and their representation. So an artificial neural network, abbreviated ANN, is a network of nodes or units, commonly called artificial neurons, connected by edges. The corresponding graph is directed. Edges typically have a weight that can be adjusted. The weight increases or decreases the strength of the connection. Artificial neurons also have a threshold such that the signals is only sent from the neuron if the aggregate signal from all input edges crosses that threshold. But furthermore, before the signal leaves the neuron, the state of the neuron, as computed from the input, is also transformed by a nonlinear function. So, furthermore, artificial neurons are aggregated into layers. So typically, units are sorted into layers, and there are many layers. And the layers may have different functions in the computation. And signals travels from the first layer, the input layer, to the last layer, which is normally considered the output, possibly after traversing the layers several times. So hidden layer may have loops, which is one variant of that is called recurrent neural networks. So, of course, the inspiration for this computational model that was outlined in the last slide is inspired by neuroscience. By the way, we believe neurons systems work in humans, in animals, and so on. The difference is, of course, while the artificial neurons are digital in nature, a real neuron is an electrically excitable cell that receives, processes, and transmits information through a combination of electrical and chemical signals. So the real neuron is a very complex machinery, in contrast to the rather simplified artificial neuron. So a real neuron consists of a cell body called the soma, and which is the body of the, and then you have the input side. So you have the input side, which is called the dendrites. So the dendrites receive the signals from other neurons. And on the output side, you have something called an axon. And an axon is the output organ, so to say, from the neuron. All of these structures are pretty branched and much more complex than in the artificial case. So an axon can also be pretty long. So this means that the axon can reach a considerable distance to the next cell to be neural cell to be affected. But the basic functionality is signals come in via the dendrites, are kind of transformed, handled by the soma, and then are output via the axon. That's the basic neurological model. So, in contrast to the artificial systems that still are of a reasonable size, the real neuron systems are huge and are in a huge scale processing in parallel. So, to give you a figure, the human brain is assumed to have in the order of 100 billion neurons. And a huge number of connections. So an actual typical figure here for the number of connection is 10,000 times the number of the neurons itself. And then you must imagine the scale of this parallel activity. Let's now be a little more concrete concerning the core components of this kind of representation. So let's look again at how we view the architecture of a neural network unit. So a unit is supposed to have a number of inputs. Actually, in the real case, in the real neural world, we talk about synapses and dendrites and so on. In the artificial case, we have simply a number of inputs, and these inputs are, of course, handling signals coming from other units. Every such input, every such edge in the neural network is given a weight. And these weights are key parameters for the connectivity and the performance of the networks. What's happened in the cell body is when receiving the inputs, there's a summation performed where the inputs are, where the weighted sum of the inputs using the weights of each input channel is performed. Then also the cell body is attributed with a threshold. And the negative value, the negation of that threshold is sometimes called a bias. So essentially what we do is that we sum the negation of the threshold with the weighted sum of the input, and then if that value is larger than 0, then the unit is ready to, what we can say, quotation mark, fire, which means to send out an output signal. But before that output signal is sent out, the output value is transformed by applying something called an activation function, which in a way modify the output value. And essentially, in all these cases, we normally talk about numerical values. So, as the functionality of an ANN unit is very important for the understanding of the whole representation scheme, let us repeat it. So, if we have an output of a unit yi, let's call it AI, this normally becomes the input to another unit j. So I is considered the predecessor of j and j the successor of I. Each connection is assigned a weight, in this case wij. Each node has an activation threshold. The negation of the threshold is termed bias, B. So for node j, we call it bj. In the body of the unit, the weighted inputs are summed together with a bias, which means that we say sum wij times ai plus bj. If this sum is greater than 0, the output of unit j is calculated, as aj is a function of the sum, where where the function is a so-called activation summon. So this is the criteria for firing, which means that outputting a signal from the unit is that the weighted sum plus the bias is larger than 0. So let's turn a minute to the so-called activation function. There are a number of those. Actually, and you see on this slide a couple of examples. Essentially, obviously, you see that there are two categories here. So, on the topmost layer here of examples, you find step functions, you find something called a sigmoid function, you find something called a hyperbolic tangent function. In all of these cases, the output level is maximized somehow. So there is a certain segment where the output value is controlled by the function, but then it reaches a plateau. In the other category, the lower part here, you see that the output is linear. So the larger the original output from value from the unit is, the larger the net output becomes. So these are two genres of functions. So now let's talk a little about the structure, given that we have delved into the functionality of a unit. So also the structures of artificial neural networks to somehow are reflected in the history of the development of the area. So as I mentioned already in the first week of this course, one of the key contribution as early as 1957 was the perceptron. But essentially, the perceptron is a very, very simple network with only an input layer and an output layer. Still, the unit functionality is in the same genre as described here. But in this case, we only had two layers. As you also may remember from the first week, this kind of simple structure was immediately successful but soon proved very unpractical, which meant that there was a big gap here from 1957 to almost 1985 when this area had a revival again. And actually in 1985 the work introduced what is called hidden layers. So while the perceptron only had an input layer and an output layer, in the early work of the 1980s, hidden layers were introduced. We will use the word deep learning later, and in a way, all neural networks that has more than two layers are considered deep. However, in the early work of 1980s, where we maybe had one hidden layer or two hidden layers, that term was not in wide use. But the introduction of hidden layers in the early 90s represented a major change. And maybe you remember from what we discussed earlier here on Bayesian networks, there's a parallel. You need an input layer. It's where in which you have to decode your input data. You need an output layer where, in a way, can harvest the results. But you also need intermediate computing elements, and these intermediate computing elements are in the the hidden layer. So then, of course, over time, when this technology developed and also computational resources became more available for this purpose, the possibility to introduce many more levels came. So what's now talked a lot about, and it's become very successful, is what is now called the deep neural networks. But essentially, the word doesn't mean much more than that there is a system with very many levels, actually. So finally, there is a slide here on different versions of neural networks. You can see the perceptron. You can see the feed-forward method, which had a hidden layer, but not many hidden layers. What is interesting is in the middle of this figure, because there is a problem with networks that only are directed in a forward manner, is that it's very difficult to represent sequences of states and also to design a memory function. So this means that one need to introduce loops in the network to handle that. So let's now look at how problem solving is carried out for this kind of representation. So you hopefully now understood the basic functionality of the units. You have also basically understood the structural properties of this representation. So when we have a problem, we have to, as always, define a set of features to express our example, as you learned earlier week. And then when we have expressed all our examples in the chosen kind of features, we have to, if we want to use artificial neural representation, we have to map the features onto the units in the input level. And depending on exactly how that looks, it becomes more or less complicated, because we should understand that the neural networks are purely numerical. So the input level is a discrete set of numerical items. So whatever input we have to map that into this discrete set of numerical values. And as I said, if we want to handle sequences and not only a single level of input, that has to be handled by a special kind of networks with internal loops. But we will come back to that later. In the same way, we also have to make the same kind of modeling for the output layer, because of course in the output layer is where we want to harvest our results. And so the output from the output layers have to be decoded back into the original feature representations. And all the above goes for any kind of problem solving. It doesn't matter whether we try to do a classification of something, we have a regression task, or if the network are supposed to generate output actions in some system. Also, all neural network computation schemes have many so-called hyperparameters that control the detailed behavior. And I mean, just take an example, selecting exactly which output function you should have in a node. And so there are many of these like internal parameters that guides the artificial neural network machinery that typically need to be adjusted to facilitate the problem at hand. But then also typically the basic flow of computation is forward feeding machinery. starting from input layer, going through the hidden layers, and ending up in the last output layer. So on the following 3 slides, I'll just show you a few examples. These examples are pretty standard ones. There are no examples with a perceptron. They are all examples from on the use of networks with one hidden layer, as it depicts in these cases. And I think the important message for all these examples is simply that the basic analysis around the domain and the features you have to consider is not different when using an artificial neural network. You still have to analyze the domain, you still have to choose the relevant feature set, and this goes for any learning approach. What you have to do here is you have to find out encoding the features in a reasonable way into the input layer. And of course, the simplest case is that all your features are ordinal, the 0 or 1, and then you can just have one input node for each of these, or you can have a numerical value, simply numerical value. If you have something more complicated, there is another mapping process. So the last example I want to show you has a different character. So essentially this is an example where the input is not a well-ordered digital feature set, but the input are images. So this means that if you want to give such a task to this kind of network, it have to solve 2 kinds of tasks. First of all, it have to solve the original task, the one where the input is well engineered in a digital form, and when you can do a classification task, you can do a regression task, and so on. In this case, the network have to do that, but also to analyze, transform the image into the digital form in a sensible way. So for this kind of network, the network not only do learning in the form we have discussed up to now, but also that it have to perform an image recognition task. So this means typically that if you want a network to do all these things, it have to be much deeper. There have to be much more room for internal computation in this kind of network. And also, for the first image recognition part, the network typically have to be specially engineered and have special structural properties to manage that task. But that we will come back to in a later week. So essentially, this example illustrates the case where your input is images, but you still want to get something semantically meaningful out of the system, which in this case is the name of the lady on the image. So let's turn to now what learning means in this kind of representation. Yeah, so as for the Bayesian networks, there are, one can say, 2 cases. So the low-hanging fruits here, the very natural learning mechanisms, are the updating of the weights of the edges, which are the key parameter of this kind of system. But also, for example, the thresholds of nodes. There could be other small things too, but the weights of the edges and the thresholds of the nodes are the key parts the key parameters that can be updated and where learning can take place. We will not delve into the learning mechanisms at this point, but one of the most earlier well-known approaches is an approach where the outcome, the result, the output from the network is reviewed externally, and after that review, feedback is given, feeded back into the system, and then the learning machinery is such that the feedback that's been fed back into the system is analyzed in such a way that credit and blame can be given to specific connections, and the weights of these connections can be increased or decreased depending on who was to blame or who was to be given credit. So this is one example of how learning can take place. But there are many options here, and we will come back to those. If we leave that, it's of course also possible to change the network in more dramatic ways. So while in the first case, the whole structure of the network is supposed to be static and only the parameters are supposed to be changed. While we also can consider the case where we can dynamically update the network with change the connections in the network, take away connections, add connections, but also introduce new nodes and new levels, which is of course the most advanced. Finally, which is not mentioned in the slide, but I will say now, that also there is attempts also to actually learn the kind of the feature sets that are actively used. So learning the selection of features is, I would say, also a possibility within category 2 here. So this is the end of this lecture. Thank you for your attention. The next lecture this week will be on the topic genetic algorithms. Thank you. Bye.